programming used to be really fun, right? Back in the time before we were writing cloud applications and before everything had to be a HTTP server that talked to a reactive front end and that sort of thing, you were just you were kind of writing code to solve whatever problem you had. Maybe to solve some sort of algorithm. Maybe you weren't even that good at it, but it was relatively fun and it was relatively easy. And then since then, it it's gotten a little bit harder, right? You had a simple program and it's written in Python or something like that, and it runs on your machine. And then in order to get it into the cloud, things get a little more complicated. First, you need to add persistence. Right, and persistence. Okay, I'm going to write some SQL. That's not too bad. And in fact, I'm going to make it a little bit better. I'm going to add an ORM. I'm going to make it a little bit more Pythonic, avoid SQL injection and that sort of thing. And that's good, right? It's a good step forward, make your program better. And then, of course, we need to put this on the internet. To put it on the internet, we need a real database. So we added Postgres. In order to make it reliable, we have a connection pooler, we have primary, secondary, we have some backups, all this sort of thing to make this a reliable thing on the internet. And you also need the server side of things, right? You need Python to be able to be interneted or cloudified. So you put it on a server, maybe in a container, you add pip and VM, and a whole bunch of other things I'm kind of skipping over, but you add continuous delivery because you're working with a team. To work with a team, you need Terraform, you need a CI pipeline, you need blue-green deployment, DB migration frameworks, some sort of container stuff. And then, of course, to make it scale, you need Kubernetes. And then once you've got Kubernetes, you've got a whole lot of stuff, right? And so this journey from this fun little program that I enjoy doing to making it in the cloud has just ratcheted up the complexity that's involved in building this application. And it's the same in the DevOps space, right? You started with virtual machines, right? And then Docker was a better virtual machine. That was great. Everyone loved that. And then it's the Docker abstraction doesn't quite handle the running a bunch of services on your local machine. So you add Docker Compose. And then the IDE isn't quite handled in that abstraction as well. Or the editor, so you add dev containers. And then, getting it running in production, it's not good enough to be running this stuff in production. You need Kubernetes. And then Kubernetes isn't enough because you need to package up these sort of these applications that you've got running on Kubernetes. So you've got Helm, and then also you've got, again, all of this stuff. And the same thing happened on front end, right? In the front end, we started with these single page apps, and very quickly you've got reactive frameworks and bundlers and minimizers and GraphQL and TypeScript even. You've got all these things. And the way that we handle that as an industry is not by saying, oh shit, there's a lot of stuff. No, instead, we handled it by specializing, right? We started with just there were engineers, and then there were back-end engineers. Right? There were front-end engineers. There were full-stack engineers who know both SQL and CSS. There's DevOps engineers and platform engineers and security engineers and growth engineers. And then we've got data engineers. We've got prompt engineers. And I'm not saying that any of these things are bad. These are good things. These are people who are specializing in the complexity of the particular areas of programming, of the stack that they're working on. And they're specialists in the tools, in the culture, in the lingo. These are all necessary things. But the problem is that we somehow scaled up our organizations and our industry to be specialists instead of ratcheting down the complexity to being where smaller teams could do it. So now you've got 100 people doing the job of 12, and you've got a menagerie of managers and engineering managers, product managers, and tech leads and architects who are trying to corral these huge teams of people with large communication pipelines and tech debts and stacks and surface area to keep in your head at one time. And this is the place where we talk about complexity, right? You've probably seen dozens of talks like this that are the complexity is out of control, and there's accidental complexity, essential complexity. There's Fred Brooks, and there's no silver bullet. Maybe there's even Aristotle in there somewhere. And I'm not going to do that, but I'm going to focus on this statement, right? Simple, understandable tools that interact well with our existing tools. This is how we're supposed to build software. You've probably seen a bunch of keynotes to talk about it. You've maybe seen programming languages that were designed around this idea of simplicity, composability, modularity, right? You do one thing and you do it well. This is the Unix philosophy. And I'm here to tell you that this is bullshit. This idea of simple, understandable tools that interact well with existing tools is the fucking problem. Because if you build things like this, what you end up with is the complexity that we have in the industry today. That is how we got here, one simple, understandable tool at a time. I want you to look at the incentives involved for companies. If you're an engineer who works at a company, you don't want to build brand new greenfield projects that solve all the complexity. You're incentivized to add a small new thing. You've got a service, and your service has a problem because your users aren't happy. The reliability is about 95%, the costs are too high, it takes too long to run, the latency is too bad, and so you say, all right, I'm going to fix this. I'm going to take a couple of weeks to do a spike. I'm bringing in Go and Kafka to deal with these problems that we have. And that's great. You spend 2 weeks to spike it, you take it to your boss, you say, this is great. Another 2 weeks, I can get this into production. Another 2 weeks, I can get the kinks out. Another 2 weeks, I can migrate the whole thing off. It's like 2-month project, 3 engineers, reliability goes up from 95% to 99% to 99.99%. Costs are down, users are happier. This is a successful project that everyone is happy with. And all you've done by doing this is brought 2 extra bits of complexity into your stack. In this case, Go and Kafka. And it's not about Go and Kafka, it's about the incentives. But you've got 30 teams that are doing this, and you've got, quarter after quarter after quarter, you've got the incentive to bring in this new thing to solve the small problem that you have, right? That's why we have these small tools, these simple tools. Simple tools are things that other people made and other people got mature and perfected and put in a package so that you can bring them into your organization to solve that same problem. And it's great when it's small, but it's terrible when it's big. And you have the same thing in industry, right? In startups. If you're a startup and you're deciding to build a whole new thing that's going to solve everything, no one's going to use that. But if you're a startup that says there's a specific problem in the logging space or the observability space or the orchestration space, and I can make a small solution that fits well with the stacks that are currently being used in the industry, that are currently being used by our potential customers, then you can make $1 billion, right? This has happened again and again and again. Huge companies are made on solving simple problems that everybody has. And this is how the tech stacks get out of control. This idea of do one thing and do it well is the problem that has caused all the complexity in our industry. And I particularly like looking at the Unix philosophy as the cause of our problem, because we've been working with this for about 40 years now. This idea of Unix programs that are made up of tools like find and sed and awk. Right? How many of us actually know find and sed and awk? How many of us really know it well? We don't. We kind of know it at a surface area, right? We know a couple of the flags for awk. We know, 1 or 2 use cases for it. And if you give us something that's fully awk, we'll have no idea at all, right? No one actually programs in Unix, and maybe this should have been a clue all along. We program using the Linux operating system. We program using new tools and POSIX and that sort of thing. But we don't write programs in Unix. We don't write, web servers that run by passing, that are written in Bash and use pipelines of data through it, because that's actually, this idea of these programs that do one thing and do it well is actually really complicated. It's hard to keep in your head. It's hard to build these applications. And we should have realized this all along, because in the 90s, we came up with this idea of batteries included, right? This was something which came from Python. It was, at the time, languages didn't really have large extensive standard libraries. They had simple stuff like in C, they had string manipulation. And Python said, we're going to put everything in the standard library. There's going to be unit code. There's going to be XML parsers. There's going to be HTTP servers. And by bringing it all in together, we were able to lower the surface area and the cognitive load that developers had. And I think that the best example of this today is Rust. Because Rust looked at systems programming and it said not just we're going to make something that doesn't segfault and that doesn't have buffer overflows and that has some nice dependent type stuff in it. But they also said we're going to make really good tools. And they expanded the surface area of what their tool could do. Because in the old days, you had to have different tools for compiling, for the build system, to do cross-compilation. Even cross-compilation actually really wasn't a thing at all, and neither was package management. Package management in the days of C and C++, and even today in the C and C++ ecosystem, is a nightmare. So for systems programming, Rust came along and said, we're going to have a package manager, we're going to have a build tool, we're going to have a command runner, we're going to have a plugin system around the whole thing, we're going to do cross-compiling. And that is so much better than what came before, that even if they didn't have this cool dependently typed stuff that allows you not to have seg faults, it would have been a much better solution than what came before. And what they did was they removed the seams. They removed you having to write the glue code. Makefiles were glue code between the compiler and your application, and you had to spend a decent amount of time on them. You even had to write glue code like autoconf and automake and all that sort of shit. They removed those seams, and by removing those seams, they allowed you not just to have to not think about those seams, but they built better stuff in the space. They built something where the dependencies could be managed a lot better, where the installation could be managed a lot better without having to think about it. And so what they did was they built holistic tools. They built tools that thought about the entire problem space that we were dealing with. They expanded the boundaries of what they were doing. Instead of doing simple tools that did one job well, they did bigger tools, holistic tools that did 4 or 5 jobs pretty well. And this is exactly what we need in the cloud. We need holistic tools that raise the abstraction level so that we're not writing programs that run in processes, on operating systems, on servers, in orchestration frameworks. We need something where the abstraction level is such that we're developing above the cloud. My name is Paul Bigger. I'm the founder and CEO and CTO of Darklang, and Darklang is a kind of a solution to this problem. We are building a programming language, infrastructure, and an editor all in one, and we're sort of taking that holistic view of how do we build cloud applications. Before I built Darklang, I was the founder and CEO of CircleCI. Before that, I did a PhD in compilers and static analysis. And so this is the sort of thing that I've been thinking about for quite a long time. How do we have developer tools, programming languages, programming environments where we've lowered the sources, or where we've lowered the amount of complexity that's involved in the system? And in order to think about this, a good starting point is to say, what actually is the complexity in cloud? And to start with, we can look at the essential complexity. And this is the essential complexity of cloud applications, but it's really the essential complexity of computing overall. We receive data, we process data, we store and query data, and we send it. This is what's involved in applications. And from the perspective of an application developer, or someone who's building things for the users, really the level of abstraction that we kind of think at is user presses the send message, a message gets delivered. And maybe there's a bit more, right? Maybe we need to look at how do our error messages handled? How are they put in the UX? Where is the message getting sent? To whom is it getting sent? And that's things that the application developers are thinking about, but that's kind of the level of complexity that we would actually like to have in our applications, the business logic. And instead, we have these three levels, and these are the three levels or the three types of complexity that we're looking at removing specifically in Dark, or the infrastructure complexity, the deployment complexity, and then the tooling complexity. And the infra complexity is relatively straightforward. I was talking about at the start of this talk, things like Kubernetes and connection pools and cold starts in a serverless world, containers, all of this stuff, all of this, Kubernetes, cloud native, building things on the cloud. This is all, I'm afraid to say, accidental complexity. The things that we're looking to do are to send messages and not, configure Kafka. We're not trying to do infrastructure as code. And the thing that I particularly like about this slide here, this is the Cloud Native Computing Foundation slide about all the technologies involved in it. And I updated it for this talk, replacing one from 2019. And in 2019, I could actually make out what it said in each of the icons when I fitted it on my slide. Now I just have no idea what anything is. I can barely even read the icons. Such is the growth of the amount of tools and the amount of complexity that we're dealing with in the cloud native ecosystem. So the second area of complexity that we're looking to remove is deployment complexity. This idea of getting code from our computers, computers as developers, into somewhere where it can be used by our users, onto the servers in the cloud. And this is particularly important because the speed of developer iteration is the defining factor in how quickly startups and how quickly tech companies and how quickly teams are moving. And the speed is inherently connected to deployment. How long does deployment take? What is the fastest time between writing a piece of code and getting it into production? And the way that it is now, many companies have it that it takes an hour. I mean, many have it that it takes 2 weeks or a quarter or something like that. But let's ignore those absurdity out there and look at the difference between having it take an hour for code to go into production versus having it take 10 minutes for code to go into production. Each journey from code being written takes at least 2 steps through the CI/CD pipeline. Then it gets deployed, and then the actual enabling of it is done by a feature flag. And so when you look at this, you have to start to think, like, if the feature flag is the enabling, what is all this other stuff? What is it for? And when you think about it, the actual amount of deployment time for code to go from your computer into production, there's no reason that couldn't be 1 second, less than 1 second, 50 milliseconds. The time between the key being pressed and getting into production by the speed of light. And of course, there's safety issues, and obviously you want to make sure that your application works all the time. But all the steps before that, if the code is enabled by a feature flag, then everything that comes before that is kind of needless complexity. And in fact, a lot of it is risk. We have a similar thing with development environments and tooling, and I talked about this a little bit earlier with Docker. But it takes a lot of time to have your team using the same tools and have that development environment matching production in a meaningful way. Things like emulators, things like making sure that containers and versions of the software are matching the same thing. Never mind everything that happens in your IDE and keeping that in sync between all your different developers. So those are kind of the areas of complexity. And before I talk about our solution, I want to give you a quick demo of what this looks like. So the first part of the demo is how we write code in Dark, write a simple HTTP endpoint that does a simple thing. And the complexity of that is basically writing the endpoint, the path of the endpoint, writing the code that is returned, and that's really it. Right, that's really all it should take to be able to get code in production. And you can see here that we have code that's fully in production that you can access from the internet. And this is what we're talking about when we say no complexity, right? You didn't have to think about where did the HTTP server go. You didn't have to think about how did this get into production. You didn't have to think about a CI/CD pipeline or clicking a lot of buttons or going through multiple different apps or even Git pushes or anything like that. Similarly, let's take this a little bit further. We're going to add a data store. We're going to save some things for data store. And the first thing I want you to see is that this is live code that's being written in production. And so what we have on the left is an actual value that came from a request that we made. You can see the requests, the traces down the left-hand side. And we're building up these traces over time, right? As we write code, we're building up the traces of a request that started several minutes ago. We're starting to build up the rest of it as we go. So we don't have to keep rerunning this code. We don't have to keep restarting it every time we make a change to it. There's certainly no compile step. And even to add a data store, all we do is we specify the type of the data. And now we have a data store for that. There's no acquiring things, but there's also no writing DB migrations and putting it into DB migration framework. And so we have all these things in a single tool. And you can see that when we run code from our editor, we're running production code from our editor. And when we do, you can see some of the safety things. So you see that we locked the database because once you've got data in the database, you don't want to be able to make changes to the schema. So these are some of the safety features that allow this instant deployment stuff to work. And as you make changes, they're just in production. And those changes you're able to see in real time. You're getting real-time feedback from this code, both from the editor. You're seeing what is the actual result of the code that I just wrote on, from the request that was made. And then, of course, when you're in production, you can easily just run it again. And those things are in production, easy to update. That's a less than 1 second update from the code that you wrote into actually using it safely in production. So I want to talk about some of the steps that were removed and some of how we thought about removing that complexity. And the first thing that we think about is what we call invisible infrastructure. You didn't have to think about where those servers were coming from. You didn't have to think about the HTTP servers. Everything was available instantly and invisibly. No infrastructure as code, no waiting for anything. We knocked down the actual complexity of building applications to the set of features that application developers think about. Right? There's data stores, there's cron jobs, there's workers. We didn't show those, but those are kind of part of the system. And then most of all, there's HTTP applications, right? Without ever thinking about how am I deploying a container to get this into production. High level abstractions pulled within this holistic tool. The second part of this is a thing that we call deployables. I absolutely do not have the confidence to deploy to coin a word like this. This was coined by Jesse Frizzelli about Dark. And deployables is sort of this idea of instant deployment without any steps in between. It's taking this huge process of getting code into production. This is 34 steps and 2 loops involved in getting code into production and whittling it down to its essentials. And its essentials here are making change with a feature flag, making change behind a feature flag, and then enabling that feature flag for your team. And we've included things like integration tests and code reviews because those are kind of optional, but most teams do them. But they're not actually essential parts of the system, but they can be layered in nice and easily to give you the safety that you need. An interesting thing about this is that when you remove the feature flag, there's no semantic difference between a feature flag that is 100% enabled for everyone and a feature flag that doesn't exist in the code because those paths cannot possibly exist. So our tool doesn't actually require you to go back through that big long rigmarole as you remove code. You don't have to open your editor, delete all the code, then make a pull request to get rid of that feature flag. It's just a single button to click. And that's the sort of thing that you get with this sort of holistic environment. Changes are instant. There's no Git branches. There's no deployment. There's no CI/CD. None of this. It's just nothing was pushed or pulled or requested. Code went straight and safely into production. And I think one of the interesting things about this deploy this stuff is the feature flags, because the feature flags replace an awful lot of stuff. They replace blue-green deployments, they replace Git branches, they replace dev environments, and of course they still solve their intended purpose of feature flags and A/B tests. And I think the insight here is that all of these things that I just described, blue-green deployment, Git branches, etc., those are feature flags at different parts of the stack. And so as you collapse down the stack, as you remove the seams between things, the various different concepts collapse into one as well. There's really no difference between branches and feature flags. They're just, one of them runs in Git and one of them runs in production. And when you collapse those two things together, then there's just feature flags. It's the same with blue-green deployment. That's something that you're doing to make sure that the code gets safely into production, but it doesn't involve enabling things for users. And so when you remove that risky step of getting code into production, you make that not risky at all. You didn't actually bring anything to the table by removing that, because that already didn't do anything. The blue-green deployment was just there to make sure that the risk that you had of deploying a new piece of software, which is semantically identical to the old piece of software, didn't take down your systems, and the actual enabling was done by feature flags. And those are, again, the same concepts. Finally, the last thing, I'm not going to dwell too much on this, is the developer environment. You saw that our developer environment had all of the tools enabled. It had collaboration built in. It was browser-based, so there was no install. There was no getting a synchronization between your computer and your the computers on the rest of your team, the dev environments on the rest of the team. It was all done in production against the real stuff, the real databases that you were using, and there was no, version skew or mismatch or anything like that. You were never working on old branches. You were never working on old dev containers. You never had to build a container to get it working. And so moving, this is something that you do. This setup is something that you do at the start of a project, but it's also something where you switch projects, you move between teams. This stuff is all brought to zero. So the complexity that we've been able to remove from this thing, there's the infrastructure complexity, there's the deployment complexity. We've got this deployment complexity down from something that's like really big and takes a long time, to almost nothing. We've got the infrastructure complexity down. This is stuff that you never have to think about anymore. These are things that are not visible to people who are building within the Dark ecosystem. They're invisible. And it's funny that you've also got some other things out of that I didn't really mention because they're not really relevant. So binaries, for example, are removed. You're not thinking about where to ship binaries anymore. But also the file system is removed. And that one's really interesting because the file system, if you're using something like Kubernetes, you're encouraged to make the file system read-only. And so the file system, something that has really high performance for reading and writing and traversing and this sort of thing that we built up over years and years and years, it's reduced to sort of a bucket store for things that are being read by the HTTP server. Similarly, the operating system, it isn't something that's visible to our users. The only thing that's visible to our users is a HTTP endpoint. And so all this stuff that we're doing for, on our platforms and for our application developers of building, containers in Alpine and, figuring out system V and, init, all this stuff is stuff that really, it just doesn't matter all that much in the applications that we're building. Even the file system and the operating systems are actually accidental complexity. And so I've talked a lot about the seams that get removed, the things that you don't need to think about when you have this holistic system. But the other thing that became apparent to us as we started building Dark was that there's an awful lot of easy wins at the boundaries. So what I'm talking about by the boundaries are the boundaries between two systems. So just like in Rust, where the build system and the compiler got sort of jammed together, that boundary where previously you had to write make files was a place that they could innovate. And they could do really good dependency analysis and that sort of thing to make sure that there was as little rebuilding as possible. And when you remove stuff for those seams, you get stuff like Deployables. This is where we're able to do this instant deployment And we're only able to do it because this language and this editor and this infrastructure were all designed for each other. And that's the kind of boundaries that I'm talking about. You don't just remove the shit that people have to deal with, but you get really, really low-hanging fruit. And the first example of this I'm going to talk about is trace-driven development. So trace-driven development is this thing that you saw where a HTTP request was made, and then we had the result of that HTTP request available as we wrote the code. And that's available because we have the runtime, the Darklang runtime running within the editor. So we can take that trace as an input, and that input can be rerun as you rewrite code. So as you write code, we're instantly rerunning it with the inputs that actually came from production users. And it provides not only this really nice development environment as you're building code for the first time, but it also makes this amazing debugger. There's two schools of thought for debugging. There's the printf debuggers, and this is sort of like the Go world, make it compile as fast as possible so that you can print. So you can add printf statements and you can see, sort of a trace of what your system does, and then you can grep for, where the right thing is happening. And the other school of thought is, no, let's restart the thing in a debugger, and then we can step through the thing and we can see the individual values of the various different programs. And both of these have their advantages, but they both have their disadvantages. You need to restart it, you need to recompile it, you need to have a reproducible test case that you're able to use to sort of debug on this thing. And what you get from trace-driven development is an awful lot less work. You can instantly see, without having to do anything, just by putting your cursor on something, what the value was at this execution time. You see it directly in your editor, not in some other tool. You see the result of your trace. You see even we fade the code that wasn't executed and we highlight the code that was executed so that you can easily see when you're looking at your program what exactly was running. And we do this by having the program, by having the language runtime know what is pure and what's impure. And then it saves, for every request that's made against our infrastructure, it saves all the impure stuff. And by impure stuff, I mean stuff that if you run it again, you're not going to get the same value. Everything from reading from a database or doing, what is the date time now or something like that. We save all that so that you're able to see it in your editor and you can have this instant, immediate, and honestly, really quite amazing debugging experience. This is one of the best things about Dark. It's one of the things our users love the most about Dark. Some other stuff that you can do when you remove that boundary, this is actually something that we haven't built, but it's a mock-up of how we think people like to think about their applications, how we like to think about our applications. If you join a job and on the first day, the senior engineer or the architect, they take you to the whiteboard and they get out a marker and they start to draw. They start to explain to you the application. They're drawing the different components. They're drawing the things that go between them, the traffic and the connectivity that go between them. And when you go to your code base, instead you have directories of files, and the files have code, and some of them are, have routes in them, and some of them have schemas in them, and some of them have models in them. And it's very different to how we actually think about our applications. And so when we start to model, when we start to think about showing the actual architecture to users, this information is stored in all sorts of different places. The traffic is stored in our cloud stuff. The templates are stored. The code is stored in our Git repository. The size and the contents of our database are obviously stored in our database. Because we don't have a holistic system, we can't build these sort of higher level tools. And in a similar way, with the trace-driven development, this is something that would be really, really hard for people to build today. If you wanted to build this in VS Code today, you would have to get the data, the data from your observability tool, and then you would have to have a language runtime that allowed you to replay that data. And neither of those exist right now. And then you would have to have it built into like the language servers so that the IDE can do it. So that's like 3 different things that need to get done by 3 different teams who are not at all associated with each other. And they would need to coordinate on this big project to be able to build something together. And you get this, that when we built our holistic system, this thing just fell out for free. It was extremely obvious that this was the thing that we should build because it was the first thing that occurred to us. I mean, it's just so clear when you've removed those boundaries that the things that you want to build in those boundaries are completely unexplored. There's so much low-hanging fruit that you get by building these holistic systems. The last thing I want to talk about here is how does AI fit into all this? Because we're moving to this AI forward world where AI writes lots of code. And I don't know the answer to this, but when you're building holistic systems, the obvious place for the AI to live is within that holistic system. When you think about how AI works and how you need models and context, and you need context from your application in order to be able to get good results, you start to realize that you need to build tools that actually understand where you are. And this is, for example, why Copilot is so good. Copilot was built to be able to take the context from all the code that you had written and run it against the IDE based on, or against the model based on your code. And this is exactly what we're going to start to see. People building AI, pulling it within the systems, not having it off on the side, instead having it within the boundaries of their programming system so that they can get better results. The way to achieve all this is to build holistic tools, to be able to remove the seams between the things. That's where the complexity lies. To be able to remove tons and tons by moving the abstraction layer higher, be able to move away from this idea of building simple understandable tools where each simple understandable tool is something that gets added to our collective knowledge, to the amount of stuff that we need to keep in our head while we build stuff. I want us to raise that level of abstraction and start developing above the cloud. Thank you.